Now that we've introduced the concept of Lagrange multipliers, we are going to attempt to apply it in a given problem. What I'd like to do is optimize the given function, f of x, y, z is equal to 2x plus 2y plus z, subject to the constraint x squared plus y squared plus z squared is equal to 9. Now please know that when I say optimize, what I'm really saying is that we are going to both maximize as well as minimize. So with that in mind, the Lagrange multipliers are set up by saying that the gradient of f is parallel to the gradient of g. Now you might pose the question, what exactly do we mean when we say g here? And g is referring to this function right here. So in the setup, g of whatever variables you have in your function is supposed to be set equal to a constant. So the fact that this is equal to 9 here lets us know that this is what our g is going to be. So first thing I'm going to do is set up the three different partial derivatives that I need to take in order for the gradients to be equal to each other. So what we're really saying here is that the partial derivative of f with respect to y, with respect to x, partial with respect to y, and partial with respect to z is going to be equal to lambda times the same three partial derivatives for g. So essentially what I'm setting up is going to be the partial derivative of f with respect to a variable is equal to lambda times the partial derivative of g with respect to the same variable. So for f, partial with respect to x is simply going to be 2x. Everything else up there was a constant. Additionally, this will be lambda times partial derivative of g with respect to x. Now in this case, that'll give me 2x, and the rest is simply going to be a constant. Doing the same thing for y, partial derivative of f with respect to y is going to be equal to 2. And the partial derivative of g with respect to y is going to be 2y. Finally, the partial derivative of f with respect to z is simply going to be 1. The other two things are constants and will become 0. This will be lambda times the partial derivative of g with respect to z. It'll be 2z. Now essentially what we have here is an equation with, a system of three equations with four variables. The good news is we can toss in this x squared plus y squared plus z squared is equal to 9 to turn this now into a system of four equations with four variables. Now I will state for the record that you should check to see whether or not each of your variables is capable of being equal to 0. You'll notice that if I were to plug in x or y or z is equal to 0 in any of these cases, it would contradict the first three equations. Plugging in x equals 0 would give me 2 equals 0. That's a contradiction. Plugging in y equals 0 would give me 2 is equal to 0, which is a contradiction. And plugging it into the third equation would be 1 equals 0, which is again a contradiction. So we'll make a little note here that says x, y, z, and for the same reason, lambda are all not equal to 0. Now this is usually an important point if you're going to perform the algebraic manipulation of dividing both sides of an equation by any of these. I think that our best bet is going to be to solve each of these equations for x, y, and z, plug the resulting expressions into the last equation here, and then solving for whatever variable we get. So from the first equation here, we're going to get that x is equal to, if we divide both sides by 2 lambda and reduce, that'll be 1 over lambda. From the second equation, we'll get the same, y is equal to 1 over lambda. And from the third equation, we'll get that z is equal to 1 over 2 lambda. Now what I'm going to do is take each of these expressions and plug it into this equation here. So we'll do x squared plus y squared plus z squared is equal to 9. X is now equal to 1 over lambda. Y is now equal to 1 over lambda. And z is equal to 1 over 2 lambda. Next up, let's square each of these. This will be 1 over lambda squared plus 1 over lambda squared plus 1 over 4 lambda squared is equal to 9. Now if we get a lowest common denominator and add all of these fractions together, we will wind up with 9 divided by 4 lambda squared is equal to 9. Multiplying both sides by 4 lambda squared and dividing both sides by 9 lets us know that 4 lambda squared is equal to 1. 2 more steps of algebra will let you know that lambda is equal to plus or minus 1/2. Now, it's good that we got two different values for lambda here because one of them is going to be maximizing our function, the other is going to be minimizing our function. So in the event that lambda is equal to 1/2, we can then go back to the substitutions that we made for x, y, and z and plug these in. So x will be equal to 1 over lambda, which will give us 2. Y will be equal to 1 over lambda, which will give us 2. Z will give us 1 over 2 lambda, which will simplify to be 1. F of this value, or these values, 2, 2, 1, will result in 2 times 2 plus 2 times 2 plus 1. This 9 represents the maximum possible value of our function f. We're going to demonstrate why this is maximum by plugging in lambda is equal to -1/2. Actually, all of the algebra turns out exactly the same with the difference that each of these values is now going to be negative. So we'll get x is equal to 1 over -1/2 to give us -2. Y is equal to 1 over -1/2, which gives us -2. And z is going to give us 1 over 2 times -1/2, which gives us -1. Plugging that into the given function, this is going to be f of -2, -2, -1 is equal to, for the exact same work from above, this will give us -9. Normally, if you have a lot of values here, whichever one is largest is your maximum value, and whichever one is most negative or smallest, that'll be your minimum value.